Hey guys, welcome to the session. I'm HASHWANTH S and I will be teaching you guys deadlock handling mechanisms in detail today. So let us see the prerequisites and agenda for this lecture. The prerequisites are you should know what is a deadlock and you should be aware of the conditions of deadlock. You should also know what is resource allocation graph, that is RAG. The agenda for this lecture are I will be teaching you guys deadlock handling mechanisms in detail, and I will be teaching deadlock avoidance with resource allocation graph algorithm and also with Banker's algorithm with a small example. We will be also covering wait for graph and how to convert resource allocation graph into a wait for graph. In the end of the section, I will be teaching you guys some gate questions, and also I will be providing you with some questions for practice. Let us hop into the lecture. I will not be deeply going into the prerequisites, but I will teach a outline of the prerequisite things. So first thing is introduction to deadlocks. I will start saying this with a small example, real life example. So I think you guys can see this diagram. In this diagram, all the four cars are blocked that they can't go to the other side of the road. Like you can see this car wants to go this side of the road, but this car is blocking this car. This car can either go front or either go back to make sure that this car goes to the other side. But this car cannot go front because there is another car blocking this car. So this car can go back, but this car is refusing to go back. Okay, so I think you understand. I hope you are understanding that this car needs to go to this road, but it is blocked by this car. In order to go to this road, side of the road, this car has to move forward or move backward. But it can't move forward because another car is blocking this car. But it can still move backward. But it is refusing to move backward, which makes this block. And this is called deadlock. And this state where the cars are refusing to move backward and waiting, it is called deadlock state. So it is a situation when two processes, that is, example, you can say car. This car is a process. So it is a situation when two processes sharing the same resource or effectively preventing each other from accessing the resources. That is, the processes are the cars and the resource is the road. So these two processes are sharing the same resource, that is the road. These two cars are sharing the same road, and one of them is preventing the other, and the other one is preventing the other from accessing the road. So this is deadlock. So take two processes P1 and P2. P1 is requesting resource which is already allocated to other process, and P2 is requesting a resource which is allocated to P1. So both the processors are still in waiting state. This state we call it as deadlock state. I hope you guys are clear with deadlock. Let's move on to the conditions of deadlock. These are the four necessary conditions of deadlock. The four necessary conditions are mutual exclusion, hold and wait, no preemption, circular wait. I will not be teaching in detail about these things in this lecture since these are the prerequisites, but I will give you a small outline about these conditions. What is mutual exclusion? At least one resource must be held in non-shareable mode. That, for example, take the same car and road. The car is a process and the road is a resource. So the road must not be shareable. Okay. In that case, it is mutual exclusion. The road must not be given. Like must not be there should be no way for the other car to move. That is not shareable. So that is called as mutual exclusion. The next thing is hold and wait. Process holding one resource and waiting to acquire resources. Let me go back and say this. You can take this car, it wants to go to this side of the road. So it is in a waiting state. It wants its other side, it wants to go to the other side, which is a resource. The other side is a resource. So it wants its resource and it is in its waiting state, not allowing this process to go to its resource. That's what hold and wait. No preemption. Okay, first of all, what is preemption? Preemption is taking the things, like taking something forcefully from another person. Like if you can take a person, two persons, and one person is having a pen, and the other person is taking the pen forcefully from this person. This is called preemption. So then, what is no preemption? It is opposite. The opposite is not taking the pen forcefully from that person. So the resources cannot be preempted, cannot be forcefully taken. And the next thing is circular wait. Each process must be waiting for a resource that is being held by another process. Okay, so every process, like take any process, for example P1, it is waiting for a resource, and the resource is being held by another process. Like take a P1 and P2. P1 is requesting for a resource R1, and the R1 is with P2. So what does it mean? P1 is waiting for R1, which is being held by another process P2, and this is called circular wait. So let's hop on to the main topic that we are going to discuss in this lecture, that is deadlock handling mechanisms. So there are four deadlock handling mechanisms: deadlock prevention, deadlock avoidance, deadlock detection and recovery, deadlock ignorance. In real life also, if some problem comes, then basically these four are used to solve the problem. Like in real life, if I have some problem, then I might try to prevent the problem, or I might try to avoid the problem, or I can detect the problem and recover from it, else I can ignore the problem. So we can easily relate it with our real life problem. So these are the deadlock handling mechanisms. So let us go in detail about these mechanisms. The first one that we are going to say is deadlock prevention. If we can violate any of the four necessary conditions, that is mutual exclusion, hold and wait, and etc., no preemption, etc., those are the four necessary conditions. So if we can violate any of the four necessary conditions at any time, deadlock can never occur in the system. So what does it mean? Like if we can eliminate, if we can remove the four necessary conditions, any of the four necessary conditions, then deadlock will never occur in the system. So the strategy behind the deadlock prevention is to design the system in such a way that the possibility of deadlock is excluded. Like what does it mean? Like we are making a system that will prevent the deadlock from coming. Like the system will not have deadlocks because we are preventing it before the execution itself. How? By removing the four necessary conditions, any of the four necessary conditions. So let us see the prevention techniques. As I said, the four necessary conditions: mutual exclusion, hold and wait, no preemption, and circular wait. So what did I say about deadlock prevention? Eliminating these four conditions, that is removal of mutual exclusion, removal of hold and wait, removal of no preemption, and removal of circular wait. So removing any of these four things will prevent us from deadlock. So let us see in detail about these four things. The first prevention technique is removal of mutual exclusion. Okay. So what did I say about mutual exclusion? Do you guys remember? I said That mutual exclusion is the thing that where the resources are not shareable, right? So then what is removal of mutual exclusion? Making all the resources shareable. That's it. Like the mutual exclusion is where the resources are not shareable. So what will happen if you remove the mutual exclusion? The resources are shareable. So we want to make all the resources shareable in order to remove mutual exclusion. But there is a problem in this. This is not possible. This is impossible and it is not so easy. We cannot make all the resources shareable, which is a difficult job. Removal of mutual exclusion is difficult and impossible. So let us go to the next one, removal of old and weight. A process must acquire all the necessary resources before execution starts. Like take a process P1, before the execution starts, it must get gather all the requirements, all the resources. Like if you are going to write the some assignment work, okay, so regarding some topic, I need to collect all the necessary resources before I start writing it, right? But in this case, it is not implementable. Why? Because we don't know what resources we need before the execution. Like if we say we are going to write an exam, we can take pen, pencil, paper, scale, everything because we know the resources that we want. But in this case, we don't know what are the resources that we need for the execution. So the first point is not possible. So let us go to the second point. If process holding some resources requests for additional resource, then it must release the acquired resource. Like let me say example. I am having two monitors in my hand. Okay, two monitors in my hand, and I need a printer now. So in order to take the printer, I need to release the monitors so that I can take the printer because my hand is full now, so I cannot take the printer. So that's what this means. Like if the process holding some resources, the resources are monitors and the process is me. So if I am holding some monitors and I want additional resource and the additional resource is printer, then I must release these monitors to get the printer. So that's what the second point is. But there is a major drawback of this, that is starvation. Okay, let me say what does it mean. Like if we follow this thing, the process has to release the resources many times. Like every time it requests for additional resource, it has to release the acquired resource. So how many times it can do? We need to think about it, right? It can't do many times, which will become as a drawback. Because if we are having more resources, like if you're having like 50 or 100 resources, then it is difficult to release the resources each time when we are requesting for an additional resource. Like I cannot take the same example. I'm having the monitor, I need printer, so I'm releasing the monitor and I'm taking the printer. After some time I need the monitor again, so again I have to release the printer and get the monitor. So how many times I can do this? If it keeps on going and I need the additional resource every time, every 5 minutes. So that is the drawback, which is starvation. So the next point is wait time out. It is waiting for another resource for some time bound. Example, I am having the monitor and I need the printer. Okay, so I can wait for the printer to come to me for some time bound. Like I don't want to release my monitor. Okay, in this case I don't have to release my monitor, I can keep the monitor but still wait for the printer to arrive. Okay, so there are two cases in this, best case and the worst case. What is the best case? If I get the printer within the waiting time, then that is the best case. The worst case is if I request for the printer and I'm having the monitor and I'm in a waiting state, but the printer does not arrive. So after the timeout, I need to release this monitor, which is like the second point, like releasing the accurate resource for requesting the additional resource. So I need to release this monitor after the timeout. So that is the worst case. So let us see the next thing, removal of non-preemption. So as I said, preemption is forcefully taking the resources. So non-preemption is no preemption. Sorry, no preemption is the opposite of preemption. So let me say example. In a traffic, you are waiting. Like there are 10 vehicles waiting in the traffic. But suddenly an ambulance comes. So what will happen next? Everyone will be away and the ambulance will go forward in spite of the traffic, right? So that is how this works. Like the resources can be preempted from processes. If you see the first point, the resources can be preempted from the processes. That is, the resources can be forcefully taken from the process. That I want a pen and my friend is having the pen. Okay, but he's not giving me the pen. He's holding the pen. So I can forcefully take the pen from him. Okay, here I am the process and he is one of the process and the pen is a resource. So I can forcefully take the pen. That is, the pen can be preempted from my friend. The next thing is process holding some resources and request for another resource that can't be immediately allocated, then all the accurate resources will be preempted. I think you guys remember this that we saw in the removal of old and wait. What does it mean? Like if we are holding some resource, if I am having a pen, if oh no, take an example of pencil. Okay, I am having a pencil and I am requesting for eraser, and the eraser can't be immediately allocated to me. So in this case, I can forcefully take the eraser from the other process, right? Um, so let us go to the third point. Process request a resource. So I am the process, I am having the pencil, and I am requesting the eraser. So if the eraser is available, then it will be allocated to me. Okay, so I can take the eraser. But in case if the eraser is not available, allocated to some waiting process. That is, I can preemptively, like I can forcefully take the eraser from the process. But the eraser that is being held by the process, like the process which is having the eraser, should be in waiting state. That is, what is in waiting state is like I need a eraser. Okay, I am not having the eraser. I am waiting for the eraser. So that is waiting state. Okay, so the process, the other person who is having the eraser should be waiting for some other resource, some other thing like pen or scale. Okay, in that time, if they are waiting only, if they are in the waiting state only, I can forcefully take the eraser. If they are in the running, if they are a running process, that is, if they are using the eraser, that is a running process, running state. I can't forcefully take the eraser because it is in a running state. So I can only preempt resources in waiting state, and the process should be a waiting process. Okay, so and the removal of non-preemptive. I was talking about this, right? This is for high priority or system processes. Like high priority or system process undergo these things. Okay, let us go to the next thing. Removal of circular weight. Okay, so see this diagram. The P1 and P2 are process 1 and process 2 respectively, and R1 and R2 are resource 1, resource 2 respectively. So what we have to do in this case is we have to allocate a number, integer number, to the resources. Okay, let me give R1 a number of 1 and let me give R2 a number 2. Okay, so I need to allocate an integer number to these resources. Take this example. We have a printer, CPU, memory, CD drive. These four are the resources, R1, R2, R3, R4. So we are allocating a number 1 for printer, 5 for CPU, 6 for memory, 7 for CD drive. So we are allocating a number to the resources. Okay, so see this table. I am the process one and I am having CPU, that is 5. 5 is CPU. Uh, I can request only for 6 and 7 when if it is strictly increasing. Okay, so let me say about this once. There are two methods that you can undergo for this process. One is strictly increasing, that is, the resource that you want must be greater than the acquired resource that you haven't. If I am having a pen and the value of the pen that I gave is 1, so I need an eraser. The value should be greater than 1 in order to get in order for me to get the eraser. That is strictly increasing, and strictly decreasing is the opposite, that I am having the eraser. Okay, that is given as a number 5. I need a pen now. The pen should be lesser than the value of this eraser. The eraser is 5, so the pen should be 1, 2, 3, 4, like that. Then only I can take the pen. So we can use either of these topics. If you are going to use strictly increasing, then we should be using strictly increasing all over the process. If you are going to use strictly decreasing, then we should be using strictly decreasing all over the process. I have taken an example for strictly increasing. So now I have CPU. Okay, that is 5. So if I want to give a request, I can only give request to 6 and 7, because 6 and 7 are greater than 5 and 1 is not greater than 5. Since I am following strictly increasing, I can only get 6 and 7. But if it is strictly decreasing, I can request only 1, that is printer. I can't request memory and CD drive, because 6 and 7 are greater than 5 and 1 is the only number that is less than 5. So in strictly decreasing, the value that we are requesting should be less than the accurate value. In strictly increasing, the value that we are requesting should be greater than the accurate value. So take the next example, 1 comma 6. So I am having printer and memory. This process is also strictly increasing process. Okay, so in order to get 5, like I need CPU now. So in order to get 5, in order to give a request to 5, I need to release 6. Why? Because 6 is greater than 5. Okay, 1 is less than 5. So if, for example, remove this 6. Okay, don't forget this 6. I am having only 1, and it is a strictly increasing function. I can take 5 because 5 is greater than 1. So I can request 5, but I cannot request numbers less than 1. Okay, so if you remove 1 and say 6, 5 is lesser than 6. Okay, if it is a strictly increasing function, I can't request 5 because 5 is lesser than 6. I can request only the higher numbers than 6. Example, CD drive. I can request for CD drive, but I can't request for CPU. But in case if it is a strictly decreasing, I can request for CPU because 5 is less than 6. So in this case, we have two things, 1 and 6, printer and memory. So in order to get 5 in a strictly increasing function, I must release the 6, remove the 6, and then get the 5. So that after removing 6 and getting 5, I will be having 1 comma 5. Okay, if this is strictly decreasing, then what will happen? I will be having 5 comma 6, because I will be removing this 1, since 1 is lesser than 5 and not greater than 5. If it is strictly decreasing, since this is strictly increasing, I am removing 6 and getting the request of 5 and allocating 5 to me, and I will be having 1 comma 5. So here you can see, to request resource or j, it's an or value, a process must first release all resources such that the resource value is greater than or equal to the requested resource value. This is for strictly increasing. For strictly decreasing, it is the opposite. I hope you guys are aware of these four things: removal of mutual exclusion, removal of hold and wait, removal of no preemption, and removal of circular wait. Let us go to the next handling mechanism, that is deadlock avoidance. Okay, let me say with an example. Okay, I'm a person. Okay, I'm just in my home. I'm in my house. I came to know that by Sunday, 10 guests are coming to my house. Okay, and the guests has arrived to my house on Sunday, and I need to offer them some juice or water or tea, coffee, something, some drinks. But I'm having only 6 glasses. I don't have 10 glasses, but the guest count is 10. So what I can do? Either I can give 6 glasses, 6 juices to 6 members, and then wait for them to finish, and then I can wash the glasses and give it to the 4 members. But this is not the way to do it. I need to give them all. I need to give all the 10 persons 10 juices. Okay, but I am lagging with 4 juices, 4 glasses. I have just 6 glasses, so I can provide only 6 juices or teas or coffees or water. Okay, whatever thing. So in this case, if I know if I know that the guests are arriving by Sunday, like take today as Friday or Saturday. Okay, so today I'm okay. Take Friday or Saturday, any day. I'm there, and the guest said that they will be coming on Sunday. So now I have this information. The guests are coming by Sunday, and I have this information. How many guests are coming on Sunday? Like I have this information that 10 guests are going to come on Sunday, so that I can check whether I have whether how much glasses I have. Then I came to find that I have 6 glasses. So what I can do? I can ask them to come the next Saturday or Sunday, or buy the extra 4 glasses and keep it ready for the Sunday. Okay, but if I don't have the information, then there arises this deadlock. Okay, so deadlock avoidance. I need to avoid the deadlock before deadlock occurs. Okay, in this case, system maintains some database using which it can take decision whether to entertain a request or not, just to be in safe state. That is, the system should maintain the database of information. That I should maintain the information database that the guests are going to come on Sunday, and then I have to decide based on the based on the thing that I need to be in safe state, right? So that safe state is nothing but a state which does not lead to deadlock. Like if I am in the safe state, nothing will go wrong. Like safe state is having 10 glasses. If 10 guests are arriving and I have 10 glasses, then I am in safe state. But if I am having only 6 glasses, then I am in unsafe state. That I need extra 4 more glasses. Okay, so that's what they are saying here. And the next point is system analyze the database to determine whether granting a request can lead to deadlock in future. So the system will analyze the information whether to grant the request or not, considering whether deadlock will come in future or not. So if deadlock will not come in future, if this thing will not lead to deadlock in future, then it is granted. Otherwise, keep pending until they can be granted. So if I am having 10 glasses and 10 guests are arriving, and I move then I am the system. Okay, I am analyzing the information that 10 guests are arriving, and I'm checking whether I'm having 10 glasses. I came to know I'm having 10 glasses, so this will not lead to a deadlock. Okay, so I'm granting. But in case if I am not having 10 glasses and I'm having only 6 glasses, then then the system will be keep pending until it can be granted. Like until I am getting 4 extra glasses to fulfill the condition. Okay, so let us go to the next thing. And I would like to say the drawback of deadlock avoidance. The drawback is the process may face long delay for obtaining a resource. Like in case if the process is in a pending stage, like pending until it can be granted, this might take long delay for obtaining the resource. So that is a major drawback of deadlock avoidance. So let us see what is resource allocation graph scheme with respect to deadlock avoidance. As I said, resource allocation graph is a prerequisite, but it comes with deadlock avoidance in this case. So I'll be teaching the intermediate concept, not the basic concept yet. So in this deadlock avoidance, we'll be including a edge called claim edge. Okay, the claim edge is indicated that the process P may request resource R represented by a dashed line. Like if you are requesting, if I need a pen, if I am asking a pen from a friend, okay, then it is a request. But if I may, like if you're considering that I may ask a pen, like I'm not asking the pen, if I may ask the pen from my friend, then that is a claim state. That is, I might ask. I'm not asking, but I may ask. Okay, so that is represented by a dashed line. I will show the dashed line. Okay, so the claim is converts to a request stage when a process requests a resource. Okay, so the thing is, I'm not asking a pen from a friend. Okay, I may ask. If I ask the pen from a friend, then the claim state will go to request state. That from the claim is I am converting it to request because first thing is I may ask. Now I am asking the pen. Okay, so that is what claim age converts to request age when a process requests a resource. Request age is converted to an assignment age when the resource is allocated to the process. So the thing is, I am requesting for the pen, and if my friend gives the pen to me, that is assignment age. Okay, then if the resource is allocated to me, like if I got the pen, then I am assigned with the pen. Okay, that is assignment age. So when a resource is released by a process, assignment edge reconverts to a claim edge. So in this case, what does it mean is I got the pen and I am writing, and the work of the pen is over. So if I give the pen to my friend, okay, if I give the pen back to my friend, then again from assignment edge it reconverts into claim edge. That the same first state that where I may ask the pen from a friend again. Okay, so the last point I will come once I explain the diagram. So see this, this dashed line is claim edge, and this line is request edge, and this is assignment edge. Okay, first of all, how do we know what is an assignment edge and what is a request edge and what is a claim edge? Okay, the request edge is when a process ask or request for a resource. If a line goes from process to request or resource, process to resource, requesting for the resource, then it is request edge. If a line, if the arrow goes from resource to process, then it is assignment. That is, the R1 is located in P1. So this line is considered to be assignment edge. Claim edge. As I said, this is claimage that P1 may request R2. This is not requesting R2. Here P2 is requesting R1, but here P1 is not requesting R2. So it may request R2 in future. So it is put in a dashed line which is claimage because we are not requesting. But when P1 requests R2, then it will become as this line, like a straight line, solid line, because it is requesting then. So this will become requested. Now let me come to the last point. Process request resource, then request edge can only be converted to assignment edge if it does not form a cycle in resource allocation graph. Okay, I will explain this thing. P2 is requesting R1. Okay, so now R1 should be allocated to P2. Okay, here what we have to see is if the request from P2 to R1 is accepted. Like P2 is requesting R1, and the R1 is accepting the request, and it is going to be allocated to P2. We need to check whether it will form a cycle like this. Okay, if it forms a cycle like this, then deadlock is there. So we need to make sure it does not form a cycle. Then only we can grant the permission for this resource R1 to be allocated to R2. In this case, if we make R1 allocate to R2, there is no a cycle, right? The cycle will break because this assignment edge will go to P2, so there will be no deadlock. But so that's the case that has been mentioned here. In order to avoid deadlock, we need to make sure that it does not form, that the request edge after converting can only be converted to assignment edge if it does not form a cycle in RAG, resource allocation graph. So this is how we avoid deadlock with the help of resource allocation graphs algorithm or scheme. So next thing is Banker's algorithm. So the next thing we are going to see is deadlock avoidance with Banker's algorithm. How many instances of each resource each process can max request? Like how many resources a particular process can request at max? That is what mentioned here. The max is an 2D array. Okay. So how many resources, like how many number of resources a particular process can request at max is denoted by max. Then how many instances of each resource each process currently holds? Like currently how many resources does a process hold? Like example, take a resource as pen. Okay, I am the process. What is allocation then? How many pen do I have? Okay, that is the allocation. If I am having 5 pens, then the allocation is 5. Okay, for example, don't take 5 pens. Take, I'm having a pen, I'm having a pencil, I'm eraser. Okay, so I'm having 3 resources now: pen, pencil, eraser, and I am the process. So I'm currently holding 3 resources, and that is what is this allocation. So the allocation of me, I am the process, right? So that is 3. How many instances of each resource is available in the system? Like it is the how many resources are available in the overall system, because they made me scale. Okay, I am having just pen, pencil, eraser, but other than that there can be more resources, right? So the available thing is how many resources are available other than this allocated resources. Okay, let me go with the example so you can understand. Okay, if you don't get this clearly, don't worry, I will be explaining this with an solid example so that you guys can clear yourself in this topic. This is the example. This is how the question will be. You will be given with this snap, okay, with this table snap, and they will ask you to find the need matrix, and they'll ask you to see whether the system is in safe state, and if the system is in safe state, then find the safe sequence. The need matrix is nothing but we need to find how much is needed, okay, how much is needed by the processes, and the safe state is nothing but the state where deadlock will not the state which does not lead to deadlock, because if you are in a safe state, then we can make sure that the safe state will not lead to deadlock. Okay, if the state is there, if the system is a safe state, then definitely there will be a safe sequence in which if we follow the sequence, the system will be in a safe state. Then if you take the process p1, p0, p1, p2, p3, p4, there is a safe sequence in which if we execute this process, it will stay in safe state. Okay, that is take this thing like P naught, then we are going to P2, P3, P4, then coming to P1. Okay, or else we can go from P naught to P4, P2, P3, P1. Look, so like there are more combinations, right? in which combination, in which sequence there exists that the process will not go to unsafe state, but the system will be in a safe state. So that is the safe sequence. We need to find it. Okay. So let us go to the next slide. The first thing what we have to find is total matrix. How do we find the total matrix? It's so simple. We need to find the summation of allocation and the summation of available. Okay, so here you can see I am adding all the allocation values and finding the values. Like from for A, we can see 0, 1 plus 1, 2, 2 plus 0 plus 0, 2. So 2. And B, 0, 0, 3 plus 6, 9. So 9. Yes, C, 1, 5, 6, 6 plus 4, 10. And D, 2, 6, 6, 12. So this what I got for allocation. And the available is 1520. Okay, don't worry, this is what the question is. Like in the question itself we will be getting these things, the allocation available. If we don't have the available, we will be having for sure the total. Okay, we might have the available or the total. Okay, if we have the total, what we will do, we will subtract the allocation with the total matrix in order to get the available. So here we are having the available and allocation. So we need to find the total matrix. So allocation plus available, which gives us 2 plus 1 3, 9 plus 5 14, 10 plus 2 12, and 12 plus 0 12. So this is the total matrix. Okay. So let's go on finding the first subdivision, need matrix. So how do we find the need matrix? There is this simple formula, that is allocation minus max. That is the max is the max value and the allocation is the allocated value. That the max is, like for take example, I can max have 5 pence, but I am allocated only with 3 pence. That is, I am having only 3 pence. So what is the need matrix? 2, because the max is 5. I can have 5 pence, okay, but I'm having only 3 pence. So the the need is 2. So the same thing is here, allocation minus max into 2 positive, or we can write it as max minus allocation. Okay, if you are minusing allocation minus max, then we might get negative values, so we have to change it into positive. So the thing is that for the need matrix, what we'll be doing is we'll be subtracting this value with this value. Okay, like see 0 minus 0 0, 0 minus 0 0, 1 minus 1 0, 2 minus 2 0. Okay, so next thing is for process 1, 1 0 0 0. So 1 minus 1 0, 0 minus 7 is minus 7, but since we have to change it to positive, it is 7. Else you can take it max minus allocation also. If in case you can see 7 minus 0 7, 5 minus 0 5, 0 minus 0 0. Okay, in both ways you can do. And the next one 1 2 1, 3 3 0, 5 5 0, and 4 6, it is 2. So similarly, we'll be finding for all the four processes. Like take the fourth process, 0 0 6 0 6, 5 1 4 6 4. We are getting 2. Okay, so now we have the need matrix. Okay, so what do you have to find next? The safe sequence. Okay, let us go and see how to find the safe sequence. Forget about all these things that is filled. Okay, I will be teaching you, don't concentrate on all the things. I will be teaching you step by step. Just focus on what I am saying. Okay, the marked things, the dilated things are what we found in the previous slide. Like these are the things what we found till now. This is given in question, and the need matrix we found. So I just marked it out so that you don't get confused. So these are the things that we are going to find now. Okay, in order to find the safe sequence, okay, what we have to do is we have to run each process. Like if we are able to execute all the process without going into unsafe state, then the system is in safe state, right? So we have to execute all the process and then make sure that we get the safe sequence. So first, we are taking with iteration mode. Okay, uh, we are having 5 processes, so we can take n minus 4 process for 4 iterations. That is 5 minus 1 4 iteration. So the first iteration what we will be doing is we are having this available, right? So we will be checking this available. We will be comparing this available with this need matrix. Okay, whether the available fulfills the need or not. Because this is available. Like if we are total, we have 10 pens, and the max I can hold is 5, and I'm having 3 pens. I'm having 3 pens, but the total is 10, right? So the available is 7. Okay, so the need matrix of me is 2. So whether this 7 can fulfill my need, okay, the fulfill the 2 pens, yes, it can fulfill, because there is 7 pens available, but I need only 2 to fulfill my max. Okay, so let us see. The first thing is available is 1520. A is 1, B is 5, C is 2, D is 0. Okay, for the first iteration we are going with the process 0. There the need matrix is 0 0 0 0. Okay, what does it mean? There is no need, okay, of resources. So in this case it is pass. Okay, if it is pass I put 1, and if it is failed I put 0. Okay, so in this case we have fulfilled the need. Okay, then it is 1. Take the next thing, 0750. A is 1, A is 0. Okay, A is fulfilled. B is 5, but B is 7. We need B 7, but we are having only available 5. Right? So in this case, we cannot fulfill the need matrix. So we fail. Put 0. See then to the next process. 1002. We need to fulfill this. It fulfills ABC, but it couldn't fulfill D, because D needs to, but we don't have anything. We just have 0. So it is also failed 0. Next thing is process for process 3 is need 0020. In this case, we can fulfill the matrix since 1520, everything is included within this. Like you can see that A is 0, but we are having 1. B is 0, but we are having 5. C is 2, but we are having 2. Okay, D is 0, and we are having 0. So it fulfills all. So it is pass. We can put 1 here. So the next thing is process 4. In process 4, you can see the need matrix is 0, 6, 4, 2. The available matrix is 1, 5, 2, 0. So A 0, we have 1 pass. B is 6, but we have only 5. So this fails and we put 0. Okay, so in this case, the saved sequence, the first thing can be P naught or P3. Okay, you can either take P naught or P3, but I will be going with the order. Okay, like if you take P3, then you can add P3 to the save state, and then you can follow the step that I am going to teach now. If not, you can also go with P naught. Either of the values is okay. But I will be going in order now. Okay, I will take P naught. Okay, so P naught is our first sequence number P naught. Now what we have to do is we have to we have to sum this available with the allocation of P naught. Okay, so we have to add this to this 0 plus 1 1, 0 plus 5 5, 2 plus 1 3, 2 plus 0 2. So this is the available thing now after finding the first safe sequence thing, first safe sequence process. So we are adding the allocation of the first P naught process with the available. So now we have 1532. Now again we have to go to the iteration 2. Then we have to check all these processes whether we can fulfill their needs or not. Okay, A is filled, the P naught is filled. Okay, 1. Then come to 2, 0750. A is 0, pass. B is 7, we have only 5. Oh no, we can't fulfill this need because we are having only 5. So it is a fail again. Then P2, this time we can fulfill the need of process 2, because you can see 1 1, yeah, it needs 0, we need 5. It needs 0, we need 3. It needs 2 and we have 2. So this is now passed. Okay, the next thing is P3. It is already passed, so it will pass this also. So this is passed. And the last one is not passing because the B value is 6, but we are having only 5. You can see here in the second box, we are having only 5. Okay, now we got next two, P2 and P3. As I said, I will go with the order. I will take P2. Okay, so I will just add the allocation value of P2 with my current available. Okay, so 1 plus 1, 2, 5 plus 3, 8, 5 plus 3, 8, and 4 plus 2, 6. So after adding the allocation of the second process in the sequence, I am getting 2886. Okay, then now I am again going with this thing. I will be checking with the process. I have already done this P naught. I have already done this P2 and P3. Okay, I have passed these cases, but I have added the into sequence only P naught and P2. So after adding this P2 value, I am going to the iteration 3 and I am checking for these values. Okay, the next thing we satisfy is 0020. Okay, so now P3 is passed, P4 is passed, also P1 is passed. Okay, P1 is passed, it's not passed, it is passed. Okay, because see, 2 okay, fulfill, 7, 8 fulfill, 5, 8 fulfill. But we are not going with P1 now because we are here now. We are not in the P1 slide, we are in the third iteration. Okay, so now we are in P2. So we cannot go back to P1 until we finish the whole processes. Okay, so now the next thing we can go is P3. So now I will be adding my P3 allocation value with this available value. So add P3 to a sequence and then add this allocation value to the available value, that is 2 plus 0 2, 8 plus 6 14, 3 plus 8 11, 2 plus 6 8. So the now current available after the sequence P0 P2 P3 is 2 14 11 8. Again just go to the iteration and now go to the P4 and add the allocation value of P4 to this available. What we will be getting? 202, 14 0 14, 11 1 12, 8 4 12. Okay, now what's the process is pending? Now look for the process which is pending. P1 is pending. So now finally add the allocation of P1 to this available, that is 2 plus 1 3 and all are 0. So add the same things, 3 14 12 12. So after adding the processes in the sequence, we'll be getting P1 P0, P2, P3, P4 and P1. If we follow this safe sequence, then the system will be in safe state. You can see the available final available thing, right? So the total in first, what we found for the total is 3 14 12 12. So finally in the available thing we arrived with the total matrix 3 14 12 12. Okay, so let us go to the next thing. The next handling mechanism is deadlock detection and recovery. After deadlock occurs, some algorithms will be applied to detect the deadlock, and after that, some techniques will be applied to recover from it. So, in this mechanism, deadlock detection and recovery, the deadlock should be there. Like it should not be coming or it should not be coming. Okay, it should not be coming after this thing. Already the deadlock should be present in the system, then only we can detect the system. Like if you have virus only, virus in your body only, you can detect whether the virus is there or not. Okay, if you don't have the virus, there is no use of detection and recovery, right? Because you don't have the virus. So after deadlock occurs, as soon as the deadlock came, then only we have to detect the deadlock and then recover from it. Let us see the deadlock detection algorithms. These two are the deadlock detection algorithms. Okay, if single instance of resource is there, then we are going with wait for graph algorithm. If multiple instance of resources are there, then we will be going with the Banker's algorithm. I hope you guys remember Banker's algorithm. Okay, it is same as that we discussed with the avoidance mechanism. So I will be saying what is wait for graph in this lecture. Okay, if there is a single instance of resource after deadlock occurs, then we will be going with this wait for graph WFG algorithm. Okay, if cycle is there in wait for graph, system is definitely in deadlock state. Okay, that let me explain what is a wait for graph. Wait for, I think you guys might remember resource allocation graph, right? Or AG. Wait for graph is similar to it but without the resources. Let me show you how the conversion works. This is the resource allocation graph. Okay, if we remove the or is the resource. So if we remove all the resources, we will be finally getting this thing only with process. So this thing without resources, only with the process, is called wait for graph. If we include the resources, then it is called as RAG, resource allocation graph. So this is how you convert resource allocation graph into wait for graph. In this case, you can see the processes are in cycle. Okay, the arrow goes to PK and PK PJ and PJ to PA and again the same. So it follows a cycle. So deadlock is present in this graph. After conversion from RAG to WFG in wait for graph, we can see that there exists a cycle which denotes the presence of deadlock. For example, let me see this. Like instead of this cycle, okay, instead of this direction, if P of I is directing towards P of J and P of K, okay, now P of I is directing towards P of K. So if it also directs towards P of J, then deadlock will not be there. But since this is in a cycle, deadlock is there. Okay, so let us go to the next thing, recovery. So let us see the recovery techniques. There are two techniques and two approaches, that is optimistic approach and pessimistic approach. Okay, so let us see in detail about this optimistic approach and pessimistic approach. Optimistic approach is preemption of resources and processes, that is forcefully taking the resources and processes, preempt some resources from process and give these resources to other process until the deadlock cycle is broken. That is, we have to forcefully take the resources from process. Like I'm having a pen, okay, and I am the process. You need to take the pen forcefully from me and give it to other process, that is other, like take my friends. Okay, I am having I am there and my friend is there. Okay, you are the third person, you who are watching this lecture are the third person. Okay, I am having a pen, so you need to forcefully take the pen from me and give it to my friend. Okay, until until when the deadlock cycle is broken. You need to be doing this until deadlock cycle is broken. That is optimistic approach. The next thing is pessimistic approach, which is process termination. About all the deadlocked process, the process where deadlock occurred, abort the process. Okay, stop the process or quit the process. And second point is abort one process at a time and decide next to abort after deadlock detection. Like if there are various process, okay, you if you're aborting one process, okay, decide for the next abort. Like I'm having the pen, okay, and I'm having deadlock. Okay, I am having deadlock and my friend is dead. Okay, uh, while aborting myself, aborting my process, before aborting my friend's process, you need to decide the next abort only after deadlock detection in my process. Okay, if you are one process, if you are one process and I am one process, okay, first the one or someone is aborting your process. Okay, aborting your process, and they need to decide next to abort. Like they need to decide whether to abort my process or not only after the detection of deadlock in your process. Okay, before detecting whether the deadlock is present in your process, they cannot abort my process. Okay, now let us go to deadlock ignorance. Deadlock ignorance is the most widely used approach among all the mechanisms. What is deadlock ignorance? It is nothing but simply ignoring the deadlock that is that has been occurred in the system. In this approach, the operating system assumes that deadlock never occurs even though deadlock occurred. It just simply ignores the deadlock. Okay, so this approach is best suitable for single end user system where the user uses the system only for browsing and all other normal stuff. So here the system will just ignore the deadlock. Like if we have some real life problem, okay, if someone is disturbing us, just ignore the thing. Okay, that is how deadlock ignorance works. It just ignores the deadlock that has been occurred. Okay, now let us see gate question. Yeah, sample gate question. So, what is the minimum value of m such that the system is deadlock free? This is the question, and this is the table that we will be given. Okay, concentrate on what I'm saying. You may not understand the question, but don't worry. I'll be explaining you this in detail. What is the minimum value of m such that the system is deadlock free? Okay, they given with five processes, that is five names: Ram, Sham, Morgan, Jia, Nitu, and the max is 3, 3, 3, 3, 3. Okay, so we need to be finding the minimum value of m. Okay, what is m? The minimum value of m is the available thing. Like example, take these five students. These are five students, and they need pen. Okay, they need pen, and the max pen they can have is 3, 3, 3, 3, 3. Okay, so we need to find the minimum value of pens that we need. Okay, to allocate to these students to make sure the system is deadlock free. For example, if you can see, they need three pens, 3, 3, 3, 3, max 3, 3, 3. How much all the three combines? 5 into 3, 15. So max is 15. So if we have 20 pens in our hand, okay, then we are satisfying the condition. Then the system is deadlock free. If we are having 20 or 25, 30, then we are also then satisfying it. We are having more than the max values. If we are having 50, it is more than enough, right? But the thing is, we need to find the minimum value. Okay, it can be any value. Like we can have 100 pence, 1,000 pence, lakhs of pence, but it doesn't matter. In this question, what they are asking, they are asking for minimum value. Okay, minimum value of m, which is how many pence that is needed in minimum number to avoid deadlock and fulfill this process. Okay, let me explain you so that you might understand. Okay, forget about this allocation. Okay, take this. This is what we have been given. Okay, see, the max value is given and the students' names are given. So now, suppose each student wants two pens. Okay, like each student, Ram wants two pens, Sham wants two pens, Morgan wants two pens, and the other both wants two pens. Okay, just allocate them with two pens. Okay, so for example, take this, like you have 10 pins in hand. Okay, for example, just take imagine that you have 10 pins, I will 10 available pens. Okay, every one of them needs two pens, so you are allocating them with two pens. Okay, so total 10 pens. You brought 10 pens. They need two pens each. So you are allocating each pair of them two pens. But their max is three. So what do we have to find first? Okay, you need to be very smart. Like I already thought this. So you need to be smart, and you should need to know what we are going to find next. Think about it. I will go to the next slide. I'll give you 2 seconds to think. I hope you found what you're going to find. Yes, we are going to find need matrix. Okay, because we are having the max and allocation. Okay, so how much do we need extra to get the max? So what is the formula for need matrix? As I said, max minus allocation, or the positive value of allocation minus max. So 3, 2, 1, 1, 1. Everyone is need is 1. Okay. Now I have 10 pins. Okay. I have allocated them 2 pins. If suddenly ROM wants 3 pins instead of 2 pins, its need becomes 2. Okay. In this case, I cannot give him. No, his need becomes 1. Okay. Now I allocated him 2 pens. If he needs all the 3 pens, the max value of him, I cannot provide him because I have only 10 pens. If I have 11 pens, if I have 11 pens, then I can give him. Okay. So we need to calculate value to satisfy need. The value which is needed to satisfy the need. Like so, if we have 10 plus 1 pence, we can satisfy all their needs. Like if I have 11 pence, if Sham asks for the extra pen, I can give him. Else if Jia asks for extra pen, I can give her. Okay. So we need to calculate the value that will satisfy their needs. Okay. Because if for example, if Ram is there, okay, I have given all of them, I have allocated all of them 2 pens. Okay, now Ram is asking for this another pen. Like I have allocated him 2 pen, but he is asking for the other pen, the needing pen. Okay, okay, the needing pen. In this case, what I can do is, like I can provide him with the extra pen that I have now. Okay, before I didn't have the extra pen, I had only 10 pens. Now I have extra 1 pen. So now what I can do is, I can give this extra pen to Ram. Okay, what will happen if I give the extra pen to Ram? Just think about it. You guys can guess it. What will happen if I give the extra pin to Ram? Then I can get all the 3 pins to me. Okay, if it reaches the max state, I can take all the 3 pins from Ram. I hope you're understanding, right? Like, wait, I will explain it again. The max is 3, and I have gave him 2 pins. The need is 1. Okay, so I have 10 plus 1 pens now. Okay, now Ram asked for the extra pen, the need pen, the extra need of him. Now I am providing him with the extra pen that I have now. Okay, if I provide him with this extra pen, then the allocation becomes 3. Right. So now I can release all these max 3. Okay, so now I can get all the 3 pens from him. Okay, so if I get all the 3 pens from him, then after that, if Sham asks me 1 pen, that is extra 1 pen, I can give him one from the 3 pen. So if I give him 1 pen, then he also becomes 3, so I can take the 3 from him. So totally I will have 6 pens. Okay. So there is a formula for calculating the minimum value. For calculating the minimum value, the formula is this. That is from 0 to n. N is nothing but the number of processes. The max summation of max minus number of processes plus 1 will give you the minimum value. That is the summation of max is 3 into 5, 3 plus 3 plus 5, 15. Number of processes 5, 15 minus 5 and plus 1 equal to 11. 15 minus 5 is 10 plus 1 is 11. So the minimum value is 11, right? So this is what we found here. You guys can see. So if you have 10 plus 1 pens, we can satisfy the needs. What is 10 plus 1? 11. So there are two methods to find that. Whether the method one is you can find it by using this formula, or what you can do is you can from the max value you can minus 1. Okay, you can minus 1 from each max value. 3 minus 1 2, 3 minus 1 2, 3 minus 1 2. Then finally you can get the allocation value of 10, right? 2 plus 2 plus 2 plus 2 plus 2, 2 into 5 10. Okay, then add a 1 with it. so that you will get the minimum value. So these are the two methods to find the minimum value in order to satisfy the condition. Okay, I hope you guys understood. If you guys do not get it fully, also don't worry. I will give you a small glimpse of it with another example. So yeah, try solving this. What is the minimum value of m such that the system is deadlock free? Same question, and I've given some different values. Okay, you should be getting the minimum value of 23. This is the answer. After you finish the solving this, you should be getting this value. If you are okay with the previous example and if you are ready to solve on your own, thank you for being here. Uh, I hope you guys enjoyed. So you can go and work out this thing. If you want again a small glimpse on how to do this, I will explain this thing. Okay, so that you can do this and find the minimum value. Okay, here we have 5, 6, 3, 7, 6, the max value. I have taught you two methods to do this. One is using the formula to find the minimum value, or by this method, just by minusing each process one, and you will get the allocation. Then after the getting the summation of this, you can add a one to it to find the minimum value. So here, let me try the second thing. 5 minus 1, 4. 6 minus 1, 5. 3 minus 1, 2. 7 minus 1, 6. 6 minus 1, 5. So 4 plus 5 plus 2 plus 6 plus 5 is equal to 22. Am I right? 4 plus 5, 9. 9 plus 2, 11. 11 plus 6, 17. 17 plus 5, 22. Okay. So here the value is 10, and we are getting here the value as 22. What I said, after the summation of the allocator, add a 1 to it. Right? So here the value is 22. So if we add 1 to it, then we will be getting the minimum value, that is 23. Okay. So if you guys use this formula also, you'll be getting the value. Come on, we'll try with the formula. Summation of max. Come on, fast, quick. 5 plus 11. What? Sorry, not 5 plus 11. 5 plus 6, what? 11. 11 plus 3, 14. 14 plus 6, 20. 20 plus 7, 27. Okay. What is the formula? Summation of max minus n, the number of processes, plus 1. Summation is 27 and number of processes 5. So 27 minus 5 is 22. Then we have to add with plus 1. So 22 plus 1 is 23, which is the minimum value. I hope you guys enjoyed this section. Please go through all these topics one on your own and try to solve many gate questions similar to this. Okay, then you guys might get an idea about it. So revise the topics once and work on more gate questions to get strong with these topics. Thank you for listening to my lecture. I hope I will be giving out some other lectures someday. And thank you for listening it calmly. Bye.